before the theory of gravity was a glimmer in Newton's imagination, the natural physics of density and buoyancy already perfectly explained why apples fall down. Quite simply, objects fall or rise based on their relative density to the medium surrounding them. Apples fall because they are denser than the air, while helium balloons rise because they are lighter. No gravity necessary. Everything seeks its relative density and rises or falls until settling accordingly. Now, this has absolutely nothing to do with gravity. Gravity is a hypothetical magnetic-like force to help explain the heliocentric universe. To claim the existence of a physical law without a single practical evidential example is hearsay, not science. How is it that gravity is so strong that it can hold all the oceans and people stuck to the underside of the ball Earth, but so weak that it allows birds, boats, and balloons to casually evade its downward pulling force? How is it that gravity holds our bodies stuck to the underside of the ball Earth, but yet we can easily walk or jump and feel no such constant downward pulling force? Gravity, both metaphorically and quite literally, just does not hold any water, not as a sound theory of cosmology, and not as a law supposedly responsible for holding in the world's oceans.
To start out, we will take a look at Earth's electrostatic field. This is important because we, along with all the matter in this known realm, are inside of an electrostatic field. The Earth itself has a measurable negative charge compared to the air above it all across the plane. As soon as you leave the surface, there is a positive charge in the air around you that grows in electrostatic potential the further you go up towards the sky. It is a steady, gradual rise in potential, which tells us, according to the laws of electricity, that we are between two Gaussian surfaces. A Gaussian surface is simply a surface that encloses or distributes a charge. If there were only one surface, the rate at which the positive potential grew would be different. Knowing that we are between two Gaussian surfaces, we can also know that certain phenomenon will take place in all matter within the electric field, or area between the two surfaces. For this topic, we will first look at polarization through electrostatic induction. Electrostatic induction is a phenomenon where the positive and negative static charges on matter are slightly separated or polarized due to the electrostatic charge of its surrounding area. If one set of the object's surroundings is positive and the other negative, the negative charge on the object will be attracted to the positive area around it, while the positive charge on the object will be attracted to the negative area on the opposite side. So here on Earth, the positive charge on our bodies is always attracted down towards the Earth, and the negative will be attracted to the air above. This phenomena creates a slight force in that downward vector, because as soon as we leave the ground, we start becoming positively charged by the air around us and are now forced towards the negative of the ground. This is electrostatic acceleration. One might think that the attraction from above and below would cancel out completely, but it is the electrostatic gradient that creates a flow from the positive above to the negative below. Think of the Earth as a flat strainer, and there is a constant flow of water from above moving very slowly over. Think of the Earth as a flat strainer, and there is a constant flow of water from above moving very slowly, always applying a force in a downward direction. This would be considered a vector. The electrostatic potential difference getting stronger as you rise from the Earth will keep a steady pressure from above at all times until it reaches the Gaussian surface above. When we reverse the polarity of the electric field and put a negative surface above a positive one, we can reverse this electrostatic phenomenon and get things to stick to the upper plate as if it were the ground. This works with all types of matter. You can move wood, iron filings, and even human hair with these forces. Believe it or not, you can even get water to bend. If the vector lines created between the two Gaussian surfaces are curved, all the matter will follow these field lines as well. In this demonstration, instead of using a flat plane, I use two circular objects as my Gaussian surfaces. You can see that as the water settles after being sloshed around by me turning the wheel on the Van de Graaff generator, it comes to rest with a curve in the surface following the electric field lines between the two spheres. This is why the ionosphere, a phenomenon that has never been created in a lab, is a theory yet to be verified, but is needed to create this phenomenon here on Earth. Maxwell himself changed Ampere's law, which stated plainly that without matter, no electrostatic field can exist. Maxwell changed it with no scientific evidence, allowing it to gather magically above our heads in free space. Density and electric potential go hand in hand. The denser something is, the more electric potential it can hold. Not that I believe in the model of the atom, but even the periodic table has a distinction on the amount of electric potential there is in the different elements. In this demonstration, I have a metal button hanging from helium balloons that keep the button buoyant just above the ground. By only adding more electrostatic potential to the button, you can see it will appear heavier and force the buoyant object down along the vector lines created by the electrostatic potential difference. Without changing the density of the medium or the object, one can change the overall weight or gravitas of the object. To do an actual experiment on the topic of gravitation, this variable of electrostatic acceleration must be taken into account at all times. Now we will take a look at how different electric potentials of gases act in this electrostatic medium we live in. Gases have different electric potentials, just like all matter does. The gas molecules that can hold more potential than those gas molecules around them are theoretically more dense and will have a stronger attraction towards the negative ground below. When these gases are carried along the downward vector by these electrostatic forces, the lighter gas gets displaced and becomes buoyant until it finds a place with the same electrostatic potential. This is why we have a pressure density gradient and are told the noble gases work their way up into the higher elevations and collect in layers above. This has not been verified by anyone I know, so at this point I cannot say if this is true or not. Through this induction, some pretty amazing things happen when large electric potential differences are applied to gases. When gases are placed into an area with a strong electric potential difference, we get the phenomenon known as ionic wind. If a person were to charge themselves up with 1 million volts of static electricity, they could blow out a candle almost 2 feet away from the gases rushing away from their fingertip because of the exceptional potential difference. We do know that when a gas loses its electric potential, it slows down so much that it turns into a liquid, like the condensation that forms on a window when it's cold outside. The gases hit the cold window and transfer their potential energy to it, trying to mediate the temperature. In doing so, the gases lose their electric potential and turn into a liquid. Down here near the surface, the system is very dynamic, with all the plants and animals breathing, low altitude weather patterns constantly cycling, and Earth releasing gases from the deep at all times. We will never see all the gases lose their potential and turn into a liquid anytime soon, I hope. Now we will get to the incoherent part of the phrase. It is called incoherent because it is not completely polarized. Like a magnet, it is called incoherent because it is not completely polarized. Like a magnet, but only slightly on its surface through electrostatic induction. A magnet, with all of its potential stored on opposite sides, would be considered coherent. Now these forces are very weak, and only apply a slight pressure along the vector they create. All other pressure mediations, such as buoyancy, atmospheric pressure, and temperature, are certainly stronger, but nonetheless, these weak electrostatic forces are ever present in the world around us, and I fear the day they may come to an end. Again, I fully understand people's reluctancy to use the word gravity when speaking of this place we live. So instead, let's call it what it really is: incoherent electrostatic acceleration. Let's teach those just finding out the nature of this world in which we live the correct way. The fact that we live in an electric realm with a static electric field you yourself can go out and measure tells us without a doubt that these well-understood laws of electricity create the downward bias phenomena we witness all across the plane. Instead of using the word gravitation, I ask you to educate yourself further on incoherent electrostatic acceleration.
So from the slow motion camera, we can clearly see that the bottom end stayed completely stationary even after you let go of the top. It waited until the whole slinky had collapsed down to the bottom before it itself moved downwards. How do we explain that?
The simplest explanation is that the bottom end is sitting there minding its own business with gravity pulling it down and tension pulling it up, equal and opposite forces, no motion at the bottom end until the bottom end gets the information that the tension has changed. And it takes time for that information to propagate down through the slinky to reach the bottom end. So it's propagating down as a compressional wave.
And we saw that compression wave travel down, and it has to reach the bottom before the bottom even knows that you've let go at the top.
Correct.
And that's when it knows to start falling.
Correct.
Okay, let's pause here for a moment. Gravitational constant. The gravitational constant, also known as universal gravitational constant or as Newton's constant, denoted by the letter G, is an empirical physical constant involved in the calculation of gravitational effects in Sir Isaac Newton's law of universal gravitation and in Albert Einstein's general theory of relativity. Now, theory, okay? Let's be clear. It is a theory. Anyways, on with it. According to Newton's law of universal gravitation, the attractive force between 2 point-like bodies is directly proportional to the product of their masses. Okay, that's the key word, okay? The masses, the mass of the object is what is attracted. So, if the slinky is stretched out, or if the slinky is compressed, it is still a mass, and therefore should be pulled by gravity, if gravity is a constant. Okay, clearly the the slinky does not react to this so-called gravity.
I just find that so amazing and so counterintuitive.
We study physics because lots of unexpected things happen, and it's those unexpected things that make physics interesting. Force acting on the tennis ball is countered by the tension force acting upwards until the information travels down the slinky that the tension has changed.
It's really quite strange because it's as though the falling slinky can support the tennis ball in a way.
That sure is what it looks like. The equilibrium of the gravity pulling down and the tension pulling up, okay, that would be broken the instant the slinky is released. Okay, the decompression would start, but the mass should still start to fall, according to gravity. Add to that the extra weight or mass, if you will, of the tennis ball, and the effect of gravity should definitely be noticeable in slow motion. The whole thing should start to drop upon release. You know, I don't know, maybe it all happens too fast. Maybe gravity isn't as constant as we thought. Maybe it just needs more time to react to the change in the equilibrium. Maybe we just need a bigger slinky.
Do you want to do another slinky drop?
That's not a slinky. This is a slinky.
That is an excellent slinky. We should drop that one.
We want to see whether a long slinky, and we're 15 metres up here, whether a long slinky works the same as a short slinky.
Because some people on YouTube don't really believe that it's going to work the same, or they want to see it.
We're about to find out.
All right. I'll go film it from the grass, and you drop the slinky.
Fine.
Okay. Here you go, Rod.
Well, did you see it?
Yeah, that was a good drop.
Did you get it?
I don't know, I think so. We got to check the cameras.
Well, I think it tended to tumble as it got right down to the bottom. I think it's going too fast and tumbling. I think we better do that one again.
We got to do it again?
Yeah.
All right.
Well, looks like time is not the problem. Gravity's just lazy, I guess. I mean, even with a monster slinky, the bottom doesn't drop when it's released. I mean, how crazy is that, huh? So, we're going to drop the slinky a second time. But first, let's look at another law of physics, okay? The law of motion. Okay, Newton's law of motion. Blah, 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 blah. Blah, blah, blah. Okay, Newton's first law. Blah, 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 blah. A bunch of mathematics. And this is what's important here. Okay? An object that is at rest will stay at rest unless a force is acted upon it. And again, an object that is in motion will not change its velocity unless a force is acted upon it. But this one here is what's really important, okay? So let's talk about that for a minute. Okay, there's two things that happen here that kind of blow my mind. Pay attention down here at the bottom of the coil, okay? And as this top piece comes down, okay, it's going to compress already here. You'll see. Let's play it through and you'll see for yourself, okay? I'm going to slow it down as it gets there. Now, you see here, it starts to compress. I'll go slowly, frame by frame. Okay? It gets denser and denser and denser and denser and denser. Okay? So that all compresses. Now, as that spring compresses, you would think that it would start to push the bottom down towards the ground, giving gravity that extra boost that it needs in order to do what gravity does, I guess. It's just ridiculous. Watch that tail end from the bottom of the slinky. Watch it whip around as it gets pulled down. And here it comes and whoop, down it goes. So you can see it's not just yeah, I don't know how to explain it, but gravity certainly isn't having anything to do with what we're looking at here. I mean, you know, Newton's first law of motion, you know, an object that is at rest will tend to remain at rest until another force is acted on it. Well, even the decompression, or compression, I guess, of the slinky as it's dropping is not enough of a force to push down on the slinky at that point. The top half, which is all compressed and dense, is falling fast, and it's not until the top half goes way past the bottom half before you see the tail whip around and get pulled down by the rest of the slinky. So gravity is not pulling any kind of mass of any kind. I mean, gravity just isn't playing a role in this. It's crazy. I think that Newton's first law of motion is in effect here. When gravity is taken out of the equation, as with this example, the transfer of motion must travel through the length of the coil before the result of the initial force is even measurable. As with the slinky, the bottom is at rest under the tension of the coil above. So when the slinky is released, the tension relaxes and the top begins to fall. But the release of the tension at the top is not a directly applied force to the bottom. So there's absolutely no force being applied to the bottom of the slinky at this point, not even gravity. So it remains at rest. Makes sense. It's not until the entire top of the slinky has fallen far enough past the bottom that there's a force applied to the bottom, as the top of the slinky literally pulls the bottom to the ground. So in conclusion, Newton's first law of motion, I'm cool with that. The slinky proves it. The bottom of the slinky simply doesn't move until there's a force exerted on it. Secondly, there's also no evidence here whatsoever of gravity. Not in any example, not even with an extra weight tied to the bottom of the slinky. There just simply is no evidence of gravity acting on any mass in any of these videos. So, thank you for your time. I hope you enjoyed the video, and I hope you learned something. I certainly did.
Things that are said to be true because we say so. Because Einstein wrote some equations that say that space-time can be bent doesn't make it true that space-time even exists, let alone that it can be bent. It's math. The human conception that ignores experiment but instead builds its knowledge around agreed-upon equations. In a Vsauce video titled How to Count Past Infinity, Vsauce states, and I quote, "This is math, not science. The things we assume to be true in math are called axioms, and an axiom we come up with isn't more likely to be true if it better explains or predicts what we observe. Instead, it's true because we say it is." End quote. Ah, it's true because we say it is. Well, good thing we can never fall victim to being fooled through math. Oh wait, it's actually a perfect way to be fooled. He goes on to say, and I quote, "Its consequences just become what we observe. We are not fitting our theories to some physical universe whose behavior and underlying laws would be the same whether we were here or not. We are creating this universe ourselves." End quote. Yes, with just math, you can create whatever you want. A physicist has said before that one can create an equation that says an elephant can hang from a cliff holding on to a branch only, and while math may say this is possible, reality knows better. He then states quite plainly, and I quote again, "So to what extent we're inventing all this or discovering it is hard to say." End quote. Very hard to say. But one thing we can certainly not say is math is reality. Let's remember that as we cover some of this math. Okay, so are we spinning? First, whenever we're discussing this topic, many people will want to use angular speed. Why? Well, because the angular speed is the same no matter where you might be on Earth, while linear speed is simply distance over time. So we can make this simple with this simple circle animation. Consider first this circle is a merry-go-round with a circumference of 100 feet. Now clearly, to anyone who can just think at all, the blue dot, and we can pretend these are horses since this is a merry-go-round, the blue horse moves faster over a given time. The green horse moves the slowest because of the equation distance over time. The blue horse is going around 100 feet in, say, 4 seconds, but the green horse, which has a much smaller circumference, is going only 10 feet in that same 4 seconds. But if we use angular speed, well then both the green horse and the blue horse have the same angular speed, but very different linear speeds. The blue horse is going 25 feet per second, and the green horse is going 2.5 feet per second, 10 times less. This makes sense. Someone at the center of the merry-go-round will definitely feel a different speed than someone at the edge. However, if we use angular speed, as most globe proponents will want to do, then the speed of the horses is all the same. They're all moving the same angular speed. The blue horse on the outer edge and the green horse towards the middle. So it makes sense why they want to use radians and talk about angular speed. The blue horse on the outer edge and the green horse towards the middle. So it makes sense why they want to use radians and talk about angular velocity because they would be the same. But we know someone at the outer edge of the merry-go-round would always move faster than someone near the middle. Here we have an article from phizlink.com that asks, if I'm on a merry-go-round with a friend and the friend is closer to the center than I am, are they going faster than I am? And the answer is no. You're going faster. The merry-go-round is rotating with uniform circular motion. That means that it rotates at a constant angular speed. They then go through a little bit of the math, which again shows that if you mean linear speed, then someone at the outer edge moves fastest. But since you're both circling with uniform circular motion, you are both moving the same angular speed. But again, the closer you are to the middle, the slower your linear speed is. The next little trick that globe believers use is to say, well, yes, we are spinning 1,000 miles per hour at the equator, but we're only going around once per day. No one could ever feel that. Well, in a sense, they're most certainly correct. On our merry-go-round here, if the blue dot moved around at, say, 1 rotation per day, you wouldn't even know it was moving. It would be so slow. But here's the trick. Remember, this merry-go-round is only 100 feet in circumference. So let's extend that to, say, a mile. So now the merry-go-round goes around 1 mile per day. Now, would the blue horse know that it was moving? Well, just barely. Not quite like grass growing, but if you looked out, you would be able to tell that you were moving. But it would be very, very slow. You'd be moving at about 1/25th of a mile per hour. But to see if we'd notice flying 1,000 miles per hour at the equator, we'd have to take that small speed we were just talking about, that 1 mile per day, and multiply it by 25,000. Think of anything moving at any noticeable speed, and then think times 25,000. It's ridiculous. Think of seeing a car drive by at 30 miles per hour. Okay, well, 25,000 times that is 750,000 miles per hour. Ridiculous. So think of a car going 1 mile per hour. Now times 25,000, that's 25,000 miles per hour. So I hope you can see how insane it is to multiply any speed by 25,000. But that's what we need to do to compare it to the speed that we're moving on the Earth. That merry-go-round at 1 rotation per day, which is 1 mile per day, needs to be multiplied by 25,000. The speed would send anyone flying off the Earth without a doubt. Let's get back to our example and how it compares to Earth. But my hope is that you realize why I think angular velocity is just not needed here and why globe believers will jump to use it. They want to use angular speed because they want to say that both the blue dot or the gray dot, the red dot, and even the green dot are all going the same speed. Angular speed lets them do that. Linear speed does not. So linear speed says that the horse on the outside has the greatest linear speed because obviously it has a greater radius. And angular speed says the speed of all the horses is the same because they all make one revolution in the same time. Okay, moving on to a global.
In 1957, the Soviet Union launched the world's first satellite into space. Since then, about 8,000 satellites have been launched. To begin making a satellite, a technician works on the internal computer that serves as the brain of the satellite, ensuring constant communication with the Earth. Circuit boards are created and double-checked by a worker. These proprietary circuit boards are a crucial component to making a satellite function. A robot makes high-tech maneuvers behind a metal cage and pre-assembles the heavier sections of the satellite. More than 800 man-hours go into making a satellite. Satellites are used for many purposes. Common types include military and civilian Earth observation satellites. Also, there are communications, navigation, weather, and space-based satellites. Space stations and human spacecraft in orbit are also considered satellites. Once the satellite is built, a team prepares to launch it. Workers attach a balloon to the main components of the satellite and fill the balloon. The balloon, or better known as a satellite, is now ready for liftoff into space. I mean the atmosphere. They release it into the sky. Above each city, there are thousands of satellites. I mean balloons. I mean satellites, creating a somewhat seamless GPS network, working in harmony with ground-based towers and undersea cables. After an artisan creates a digital painting of a satellite, a programmer then writes a complex algorithm that controls Google search results, making sure when people search for flat Earth, they only see what Google wants them to see. The programmer then uploads the digital rendering to Google's hard drive to complete the process.
In 1974, I was introduced to the late Dr. Wernher von Braun, in the U.S., the father of rocketry. He said to me, "Carol, you will stop the weaponization of space. And we have to prevent the weaponization of space because there is a lie being told to everyone that the weaponization of space is now first being based upon the evil empire, the Russians. There are many enemies," he said, "against whom we're going to build this space-based weapon system, the first of whom was the Russians."
And finally, earlier today, the Russian Federation recklessly conducted a destructive satellite test of a direct ascent anti-satellite missile against one of its own satellites. The test has so far generated over 1,500 pieces of trackable orbital debris and hundreds of thousands of pieces of smaller orbital debris that now threaten the interests of all nations. In addition, this test will significantly increase the risk to astronauts and cosmonauts on the International Space Station, as well as to other human spaceflight activities. Russia's dangerous and irresponsible behavior jeopardizes the long-term sustainability of outer space and clearly demonstrates that Russia's claims of opposing the weaponization of space are disingenuous and hypocritical. The United States will work with our allies and partners to respond to Russia's irresponsible act.
And now we hear on the news just today, this week, that they've slid in another enemy. Only this time we're going to protect our satellites.
What the Russians did today with these 1,500 pieces of trackable orbital debris poses a risk not only to those astronauts, not only to those cosmonauts, but to satellites, to the interests of all nations.
Space is a warfighting domain.
Our adversaries have transformed space into a warfighting domain.
We may even have a Space Force. We'll develop another one. Space Force. We have the Air Force, we'll have the Space Force.
I occasionally think how quickly our differences worldwide would vanish if we were facing an alien threat from outside this world. And yet, I ask you, is not an alien force already among us?
What was once peaceful and uncontested is now crowded and adversarial. We must have American dominance in space.
We too must now recognize the necessity of a space force.
Then there would be terrorists. Then there would be third world countries. Now we call them rogue nations or nations of concern. Then there would be asteroids. And then he would repeat to me, then there would be terrorists. Then there would be third world countries. Now we call them rogue nations or nations of concern. Then there would be asteroids. And then he would repeat to me over and over. And the last card, the last card, the last card would be the extraterrestrial threat. And now we hear on the news just today, this week, that they've slid in another enemy. Only this time we're going to protect our satellites. In other words, we have to have some reason to spend these trillions, to waste these dollars on a space-based weapon system, and they're all lies.
As I'm standing here talking right now, gravity is pushing me down towards the floor.
Much of the following explanation is adapted from Nobel Prize-winning physicist Richard Feynman's lecture on physics, a section called Electricity in the Atmosphere. A downward electrical current exists and consists of positive ions, molecules or clumps of matter that have a positive charge. These ions are moving slowly toward the ground. The current density from these ions is very small, around 10 microamps, or 10 picoamps, crossing each square meter or yard every second. So in any small area, there's not a lot of power. And that's the explanation about atmospheric electricity adapted from Feynman's lectures.
Tennis ball is spun rapidly, the water sprays outwards. The scientists magicians have an answer for this. They call it gravity.
And by the way, this is called gravity.
The scientists magicians are at it again, weaving their spells and telling us tales of a powerful force keeping us rooted to the earth. If gravity was such a powerhouse, then birds would struggle to fly. Insects would not be able to use wind to navigate. Monkeys would not climb and jump among trees with ease. Planes would not be able to take off from the ground. Trees would not be able to overcome gravity's pull when their growth towards sunlight and would begin to bend towards the earth the taller they became. And if gravity exists and has the power to bend and wrap the oceans around a gigantic spinning ball, then humans would certainly struggle to lift their arms and legs. Legend has it that an apple fell on Newton's head as he sat under the tree, and this was the catalyst for his great discovery of gravity, which claims that objects are attracted to large masses and gravitate towards their center. However, when they talk about gravity, what they are actually referring to is the law of density relative to mass.
Today, I'm going to show you a simple science experiment that you can try at home to learn about density. Start by taking an empty glass and tip in some water and food colouring. Then add some syrup or treacle. And I'm going to add a little bit more water to make the layer a bit thicker. Then finally, fill the glass up with some oil and leave it to settle for about 15 minutes. These liquids separate out into different layers because they're different densities and they don't mix. The syrup has the highest density, so it sits on the bottom, and the oil, which has the lowest density, rises to the top. Try dropping different objects in to see what happens. If we drop this metal nut in, which is really dense, you can see it sinks right to the bottom. But if I take this grape and drop it in, it sinks through the oil and water, but sits on the syrup. This is because the syrup is denser than the grape. Pretty cool, huh? Now if I take this plastic bottle top and drop it in, it slowly sinks through the oil and sits on the water. And finally, if I take this piece of sponge and drop it in, it sits on top.
It is a scientific fact, verified by undisputable evidence, that when objects are placed in mediums with less density, they sink, and when placed in mediums with higher density, they rise or float. For example, a rock in water will sink because the object's density is greater than the water's density, as will a ship's anchor. Likewise, helium-filled balloons rise because they are lighter than the air. Submarines float on the ocean when their ballast tanks are empty and contain air, and they sink when their ballast tanks begin to be filled with water. This is how they manipulate their depth in the ocean, by adjusting the ratio of air and water in the tanks. This is proven by filling a balloon with 50% air and 50% helium. As helium is lighter than air, and the ratios are even, the balloon remains fixed in the air without rising or falling. Again, much like the Earth's curve and spin, we do not witness smaller objects on Earth gravitating and orbiting around or being pulled towards larger objects. It seems very convenient that gravity's tendency to make smaller objects orbit around larger objects is exclusive to the globe itself and all the supposedly surrounding planets and stars, none of which we can actually see in motion or orbit. Even when you study the claims made by the scientist magicians of the so-called planets and moons, their calculations begin to work against.
Freemasonry is Satanism in disguise. Now start the clock. From Morals and Dogma, prepared for the Supreme Council for 33rd degree. That's the highest degree in Freemasonry, and written by the undisputed heavyweight champion of modern Freemasonry, Albert Pike. On page 321, he boldly states, Lucifer, the light bearer. Strange and mysterious name to give to the spirit of darkness. Lucifer, son of the morning. Is it he who bears the light? Doubt it not. Did you hear that? Lucifer is God, and do not doubt it. Come on now, stay with me. Here from the Encyclopedia of Freemasonry, written by 33rd degree Freemason, a beloved member of the craft, Albert Mackey. He tells us whose name represents the good principle in Freemasonry's secret worldview, writing under the Masonic meaning of the word pentagram. He says that the pentagram, depending on its position, represents good or evil. See how he puts the positive aspect in the first position? Good first, evil second. Good or evil, light or darkness, victory or death, initiation or profanation, Lucifer or Vesper. Lucifer is good. Lucifer is light. Lucifer is victory. And Lucifer is true initiation. See, if you're not initiated, you're profane. If you haven't figured out that God is Lucifer, you're vulgar and profane. You're stupid, in their own words. That's the beginning of their big secret. God is the devil, and we're already in hell right now. Now from the Freemason of the Century, Manly Hall. And this will make it 3 out of 3 legends of Freemasonry stating the same thing. In The Lost Keys of Freemasonry on page 76, when the Mason learns that the key to the warrior on the block is the proper application of the dynamo of living power, he has learned the mystery of his craft. The seething, surging energies of Lucifer are in his hands. Do you see?
Science cannot account for everything.
Yes, I do deny that science
So what can't it account for?
Well, had you brought that up in the debate, I had a number of examples that I was going to give. I think there are a good number of things that cannot be scientifically proven, but that we're all rational to accept. Let me list 5. Logical and mathematical truths cannot be proven by science. Science presupposes logic and math, so that to try to prove them by science would be arguing in a circle. Metaphysical truths, like there are other minds other than my own, or that the external world is real, or that the past was not created 5 minutes ago with an appearance of age, are rational beliefs that cannot be scientifically proven. Ethical beliefs about statements of value are not accessible by the scientific method. You can't show by science whether the Nazi scientists in the camps did anything evil as opposed to the scientists in Western democracies. Aesthetic judgments, number 4, cannot be accessed by the scientific method because the beautiful, like the good, cannot be scientifically proven. And finally, most remarkably, would be science itself. Science cannot be justified by the scientific method. Science is permeated with unprovable assumptions. For example, in the special theory of relativity, the whole theory hinges on the assumption that the speed of light is constant in a one-way direction between any 2 points A and B. But that strictly cannot be proven. We simply have to assume that in order to hold to the theory.
But you're missing the whole...
So put that in your pipe and smoke it.
Yeah, okay. Yeah.
So we are... None of these beliefs can be scientifically proven, and yet they are accepted by all of us, and we're rational in doing so.
The universe burst into something from absolutely nothing. Zero. Nada.
As it got bigger, it became filled with even more stuff that came from absolutely nowhere. How is that possible? Ask Alan Guth. His theory will explain everything. Well, what does Alan Guth say? In Scientific American, Alan Guth says the observable universe could have evolved from an infinitesimal region. That's a dot. He said it's then tempting to go one step further and speculate that the entire universe evolved from literally nothing. Folks, why would a sentence like this be found in Scientific American? There's nothing scientific about that statement. It exhibits incredible faith. But the textbooks teach this dot was spinning. It spun faster and faster. Finally, it exploded. The Big Bang. There are so many problems with the Big Bang. Simple physical science problems. What exploded? Where did the matter come from? Where did the energy come from? Where did the organization come from? Where did the information come from? The story he gave was so good, I got to replay the tape and hear this, 4.6 billion years ago, the planet developed a rocky crust. The chemicals got together, blah, blah, blah. Here we are. Exactly what I said earlier. That's what the theory teaches. Now, if he wants to believe that, that's fine. I don't care what you believe. But don't call that science. And don't make me pay to teach that to the rest of these kids in this university. These kids came here to learn some science, not a fairy tale like that. Thank you.